I'm going to teach you kinetic theory of gases. Okay, first one is the Boyle's law, next is Charles' law, then Gay-Lussac's law. So it's Boyle's law first. Boyle's law is P is inversely proportional to V at constant temperature. At constant temperature. Therefore, PV is always a constant, or P1 V1 is equal to P2 V2, and this is what is Boyle's law. And the graph between P and V is an indicator diagram, which you learned it in thermodynamics, this reciprocal function. Supposing they ask you a graph between P and 1 by V, it will become linear, because P versus 1 by V will be linear. That's Boyle's law. Let's go to Charles' law. Charles' law is this, where volume is V is equal to V naught into 1 plus T by 273.15, and this shows that when you take an LCM, it's 273.15 plus T by 273.15, which shows that this is the final temperature. Therefore, volume is directly proportional to temperature. So then in Aurora, they would have drawn VT graph to be a straight line where it's linear graph. However, I would like you to know this graph, which is between volume and temperature, which should be a graph like this. And exploratory, they will extend this and they'll find it to be this is 0 degrees Celsius or 273 Kelvin. This will be 0 Kelvin or minus 273 degrees Celsius, at which can you see the volume is becoming 0 at this point. This is called absolute zero. Absolute zero is only for an ideal gas, where you can imagine when the temperature is decreased below a certain point, the volume becomes 0. This is the absolute zero beyond which we cannot reduce anymore, because that's the lowest temperature, because already the volume has become 0, and this pertains only to ideal gas. So this is Charles' law. But constant pressure is a key word. At constant pressure. Next is Gay-Lussac's law. Gay-Lussac's law is similar to Charles' law, where he is doing a relation between pressure and temperature. P is equal to P naught into 1 plus T by 273.15, which shows that the pressure is also directly proportional to temperature. So it's P1 by T1 is equal to P2 by T2 in that case. That's Gay-Lussac's law. And the graph again is between pressure and temperature will be a graph like this, exploratory, absolute 0 Kelvin. And the most important point in this is at constant volume. Generally learn what is a triple point of water. A triple point of water is when water can exist in solid, liquid and gaseous state, all of them in equilibrium. Can you imagine this can occur only at a special pressure 0.46 centimeter of mercury, and also at a temperature 0.01 degrees Celsius or 273.16 Kelvin. So this triple point is something we already know. So using Gay-Lussac's law, we can find unknown pressures such as this, pressure at triple point by temperature at triple point is equal to unknown pressure by a measured temperature. Using some experiment, you are measuring a temperature, and if you know triple point we already know these two are constant values, 0.46 centimeter of mercury, and this is a 273.16 Kelvin. Therefore, cross multiplying, if you know the temperature of some measure, you can get the unknown pressures value, and that's how Gay-Lussac's law is very useful, and we are able to use the triple point of water in predicting an unknown temperature or a pressure. So that's about Gay-Lussac's law. Okay, so you know that P by T is a constant, or P1 by T1 is equal to P2 by T2, or in other words, pressure at triple point by temperature at triple point is equal to unknown pressure by known temperature, whatever. Then let's write what is gas equation. The gas equation is PV is equal to nRT, where N stands for number of moles and R stands for gas constant, which is 8.31 joule per mole per Kelvin. Mug it up. So N is nRT, and where T is the temperature, P is pressure, V is volume. N stands for number of moles. So let's write what is number of moles. Is given mass by molar mass. Okay, where given mass is 1 gram. They've considered as 1 gram. So the same gas equation, considering the given mass is 1 gram, goes about as 1 by m naught, which is the molecular mass in grams. Given mass by molar mass in grams, you know in chemistry. So you get this equation. This became like this. Another thing that you should know is you should know that N, which is number of moles, which is given mass by molar mass, or in other words 1 by m. Similarly, you should also know that the total number of molecules by Avogadro number is also smaller. N is equal to N by Na. So then therefore this can be written, okay, and also know what is Boltzmann's constant. Is gas constant per unit molecule. When you divide it by Na, you get per unit molecule. So then therefore you replace R as Kb into Na. Pv is equal to Kb into Na. Already there is an N also into T, where N is nothing but N by Na into Kb into Na into T. Thus you get a new formula. Pv is equal to N into Kb into T. Okay, so that's about this. There are various ways in which you can write gas equations. How you can change it around. This is when you use Kb, it is definitely for unit molecule because you have divided R by Na. When you write it using an R, it means for that mole. It makes sense because you have N, R is for 1 mole. You multiply it number of moles, so it makes sense there. R is for 1 mole per Kelvin, correct? And this is for unit mole when used with Kb. It should come with a small n into Kb into T. Okay, so let's go to next. Next is this is a perfect gas equation. How do you change it and write it? Then is about what is K? Pv is equal to nRT. So R is equal to Pv by Nt. Suppose they ask you to plot a graph between Pv by Nt and pressure in terms of ATM, atmospheric pressure. It has to be a constant because R is a gas constant. Should be 8.31. But however, this is applicable only for ideal gas. For normal gases like real gases, the graph will be curved like this. But higher the temperature, T1 is greater than T2, it is closer to the ideal gas behavior. This is about Pv by Nt by versus P. Next graph is the Boyle's law graph. P is inversely proportional to P. This is for an ideal gas. For a real gas, it will not be exactly this, it will be somewhere below. You can draw it like this and say it's so higher the temperature, T1 is greater than T2, it is closer to the ideal gas behavior, something like that. Okay, they will not ask you this. And then next one is about VT graph. VT graph is nothing but Charles' law, but they are putting V here and T here. But it has to be a straight line for an ideal gas. For real gases, it's not a straight line, it's going like this. Are you clear? It's going like this. So there is a variation, but higher the temperature, it's closer again. So for AC, can you higher the temperature? It's closer to the ideal gas behavior as the temperature is increasing. Can you see? So that's what it is. Only at higher temperature, the gases can behave like an ideal gas. So that completes this. So next topic is about kinetic theory of gases. The real lesson starts here. The whole lesson has been learned based on ideal gas. What are the properties of ideal gas? Assumption number 1 for an ideal gas is we already learned in thermodynamics that in ideal gas the intermolecular force of attraction is 0. We consider that there is no intermolecular, therefore there is no potential energy. The only energy that exists is only the kinetic energy because there is no intermolecular force of attraction, correct? No intermolecular force, therefore no potential energy, only kinetic energy, number 1. Number 2, I told you the molecules, the size of the molecule is negligible. The size of the molecule is negligible when compared to the negligible compared to the distance between the two molecules. When compared to the distance between the two molecules, the size of the molecule is negligible. Size of molecule is negligible when compared to the distance between two molecules. Third point, you should always consider between two successive collisions, the molecules are moving only along same straight line. Remember when I taught you this, I taught you the Vx is like this, Vy is like this. I am not saying that the molecules are going like this. The vibration is always along the same straight line. So between two collisions, the molecules always move only along a same straight line, correct? Moves in a straight line with a uniform velocity, Vx, Vy or Vz. So the molecule between two successive collisions will always move only along a straight line with uniform velocity. That is another point that you can write. I am just not saying in the same order, I am saying in a different order. And then we can also say the molecules randomly collide with each other and also collide with the walls of the container. Correct? And what else we can say? The molecules are continuously in a state of random motion. They move in all possible, each one will have all possible velocities, Vx, Vy, Vz, in all possible directions, correct? And that's enough, I think. The density should always remain a constant. Throughout, the density is considered to be a constant. Density is not varying. Okay, so those are the properties of ideal gas. Why do gas exert pressure on the walls of the container? The gas molecules, when it goes and hits the wall, there's a momentum, P initial. When it returns back, there's a final momentum. There's a change in momentum, which is P final minus P initial. Let's consider this to be P and this also to be P. You know, P final is minus P initial is P, minus 2P is the change in the momentum, and rate of change of momentum will cause pressure, will cause a force, and force by area will always give you a pressure. And this concludes that there is a pressure, there's a change in momentum, there should be a force, and force means there should be a pressure, and the pressure must result in a change in, pressure must result in, there exists a pressure on the walls of the container. So let's go to next. Very, very important question. First question in your exam paper, prove that the pressure of the gas is 1 by 3 rho V square. Pressure exerted by gas is 1 by 3 rho V square. Very, very important equation, where you draw a cube like this. Just segregate into half. To consider that half the molecule is moving towards the right side, while half the molecule is moving towards the right side. I agree that the molecule can move with Vx, Vy and Vz at all possible directions, yes, and moves in a straight line. Agreed. I am taking only the Vx component. So then along x direction, it can move in positive x direction and negative x direction. Therefore, I am bifurcating the entire volume into two, considering that if n is the total number of molecules per unit volume, then n by 2 goes here and n by 2 goes this side. Are you clear? So now let's do this. N is the number of molecules per unit volume. What is the volume for this portion alone? This is area. The distance through it's moved is Vx into delta t. Velocity is distance by time, distance is velocity into time, so Vx into delta t in a time delta t. So the volume is A into Vx into delta t, and n is the number of molecules per unit volume. So you multiply this with n and also divide it by 2 to get the exact number of molecules only on the half side. Okay, that's what is approaching that side, and you want to find the change in the momentum. The change in the momentum, I told you, is 2mv, correct, Vx, and the change in the momentum is this, where now you know this is mass of one single molecule, but how many molecules are there? This many molecules are there now. So the change in the momentum contributed to that molecule, you multiply m, n, a, Vx delta t by 2 into another Vx will make this Vx square. The 2 and 2 get cancelled. Of course, this is a minus n which I can ignore. This is my delta p, and the delta t can be brought down, which will give me my force. And next step, I can bring the a down, because F by A gives me pressure, which will give me mn Vx squared, ignoring the negative signs. You get P along x direction. P along y direction will be mn Vy square. P along z direction is mn Vz square. And pressure is a scalar, not a vector. So it's Px plus Py plus Pz by 3. Therefore, it will become mn into Vx square plus mn into Vy square plus mn into Vz square by 3. So you can take 1 by 3 out, and mn and a Vx square plus Vy square plus Vz square, which itself is nothing but magnitude of V average the whole square. So this is, and what is mn? You know, density is mass by volume. Considering unit volume, this will become 1, and m will become small m into small n. Number of molecules, mass of one molecule is m, nm. So you can replace nm, considering unit volume, you can replace it as rho 1 by 3 rho V average the whole square is a formula, provided you take it as unit volume. Very, very important, where rho can be equal to mn. Are you clear? Not mn by V, because V becomes 1. Are you clear? So this is a very, very important derivation. Next derivation is the relationship between the pressure and kinetic energy. There is no potential energy, this is only kinetic energy. And kinetic energy, you know, is half of one molecule is half mv square. But we are not talking about one molecule here. We are talking about the entire gas's kinetic energy, considering unit volume. And so this will become 1 by 2 rho v square. How? Density is mass by volume. And you know mass is small n into small m. And unit volume, you know rho is mn. And you have m here. Oh, this is about entire mass of the gas, not one molecule. Entire mass of the gas, you can replace it as rho. So half m rho. Half into m v square, where entire mass is mn, and volume you can replace it as rho because v is 1. I hope you understood. So 1 by 2 rho v square. Pressure is 1 by 3 rho v square. So let's find the ratio of these two. Let's divide pressure by kinetic energy. We will get 2:3. Therefore, pressure is 2 by 3 of kinetic energy. They call it E, they don't call it as K, they call it E in this whole lesson. This is considering unit volume. Now I'm going to multiply left hand side with volume. Why? Because considering there is a volume, the P will become PV is equal to 2 by 3 E. So from which I can write E to be, I can also write PV is equal to RT. PV to be RT considering 1 mole. For 1 mole, PV can be replaced as RT, 2 by 3 into E. Therefore, E is 3 RT by 2 for 1 mole. For 1 mole, that's the energy. Now you can divide R by Na. This is for 1 molecule per molecule, which means this will become Kb. 3 by 2 Kb into T is also the formula for energy per unit molecule. So you should understand when is the formula 3 RT by 2, it's for 1 mole. 3 kBT, which is for per unit molecule. That clarity you should have. Once you get this, you can take this formula and write energy. This is for 1 molecule, so energy can be half mv square, small m, is equal to 3 by 2 kBT. 2 and 2 get cancelled. So V square is equal to 3 kBT by small m. V therefore root of 3 kBT by small m. When kB comes, there should be unit molecule, so small m will come. But if I replace this for 1 mole, is 3 RT by capital M. Are you clear? So that's what is this, and this is called RMS velocity. Now I am introducing you to what is RMS velocity, what is the most probable velocity, and what is average. You already know what is V average. Okay, I'll just do this graph and show you. Okay, this graph is very, very important graph. But you should draw it like a mountain like this. And here, this is called most probable velocity. Next to it will be V average. Next to it will be V RMS. This is the velocity on the x-axis. This is the number of molecules. Number of molecules. Which means this is the most probable velocity, means this many number of molecules is going with this velocity. This is not the highest velocity. Can you see? This is the lowest velocity. The highest velocity is V RMS. But majority, in your class, majority have got a 60% mark. Only very less people has got 90% marks. Like that, the most probable velocity is the velocity possessed by maximum number of molecules. Okay, so then therefore, you know VMP is lesser than V average is lesser than V RMS. And I'll tell you an association. Okay, most probable V average, V RMS, you know, is a root of 3 RT by capital M. Okay, so this will be average, which will be lesser than that. So you can write 8 by pi of RT by capital M. This is most probable velocity, which is 2 RT by capital M. This is the least. So this is the way, and you can write root 2 is 2, root of 8 by pi is 2, root of 3 by 3. And that's the ratio in which most probable average and RMS velocity is varying. This graph is very, very important graph. This is called Maxwell's speed distribution graph. Maxwell's speed distribution graph. They will ask you to write a note on this very, very important question. So the next thing that I want to teach you is how to derive Charles' law using kinetic theory. You know Charles' law is nothing but V is directly proportional to T at constant pressure, right? You're going to derive this using using gas equation, which is P is equal to 1 by 3 rho V square. Okay, you know from this V square is directly proportional to T. You know from here also V RMS, can you see it's directly proportional to root T. V RMS is directly proportional to root T, so V square is proportional to T. Instead of this you can write T, and this is, I am trying to prove V, volume has to come. Volume is directly proportional to temperature. I got the temperature here. P is equal to 1 by 3 rho T. I still haven't got volume, but I can take density as mass by volume. And considering that you take this V to the other side and bring the P to this side. This shows that if these are constants, V is directly proportional to T. Hence, we have arrived at Charles' law using the pressure formula. So, similarly, we can arrive at Gay-Lussac's law. Gay-Lussac's law is about pressure is directly proportional to temperature. Take pressure's formula, which is 1 by 3 rho V square. And you want pressure on the left side, temperature on the right side, you can write V square as T. And that's all. No, this is density, mass by volume, and these are constants. Pressure is directly proportional to temperature. We are done. We are able to get Gay-Lussac's law directly from pressure's formula, kinetic theory. Similarly, what else I have to do? So you found Gay-Lussac's law. We have to find gas equation using kinetic theory. Start like this only. PV is equal to 1 by 3 rho V square. From here we have to get gas equation, which is PV is equal to nRT. We write density as mass by volume, cross multiply, PV is equal to 1 by 3 m V square. And V square is nothing but T, because proportional to T, you can replace this as T. And 1 by 3 and m are constants, therefore PV is proportional to T, PV is equal to nRT. So that's about this. You got the gas equation as well. So then last is the Avogadro's law. It's not there in book, but what did they ask you? Avogadro's law means if you take equal volume of gas at same temperature, the number of molecules will always be the same. Take gas number 1 and gas number 2. It's got has got same volume. But then N1 should be equal to N2. Number of molecules at a constant temperature T, then N1 should be equal to N2. That is known as Avogadro's law. And there is a proof for this. And you have to prove it using, again, P is equal to 1 by 3 rho V square. Such a beauty. But here, you're going to write, both of them are kept at constant pressure also. So you have to take, pressure is also same, P1 is equal to P2. So 1 by 3 rho 1 V1 square is equal to 1 by 3 rho 2 V2 square. 1 by 3 get cancelled. And density is mass by volume. So can I write mass m1 by v1 into, this is velocity square, is equal to m2 by v2 into velocity 2 whole square. This is volume. Okay, and this itself is small m into n by v1 into velocity square is equal to small m2 into n2 into velocity square by v2, but volume are the same, so you can cancel. So you get it like this. Mark this as equation 1. Next, what you do, assuming that they both have the same kinetic energy, because they are at the same temperature, no? So they both the gases have the same kinetic energy. The molecules is half m1 v1 square is equal to half m2 v2 square. Considering for one molecule, half and half get cancelled, you get this as equation 2. Divide 1 by 2. m1 v1 square will get cancelled. m2 v2 square, m2 v2 square, you get n1 is equal to n2, which proves Avogadro's law. Using again P is equal to 1 by 3 rho v square, we are able to do so many. And I also taught you, I am going to teach you what next is degrees of freedom. Next, let's go to the topic degrees of freedom. In degrees of freedom, supposing there is a monoatomic particle, it can vibrate along x direction, it can vibrate along y direction, vibrate along z direction. The 3 degrees of freedom. It's easy for me to say for a monoatomic. For a diatomic, I won't know how to say the degrees of freedom. So in chemistry probably you know, but in physics we have memorized a formula to find the degrees of freedom, which is 3n minus k, where n stands for the monoatomic or diatomic, k stands for the number of relation, which will give you degrees of freedom. Let's say monoatomic. For monoatomic, degree of freedom 3 into 1 minus 0 relationship. In one molecule, you can't have any relationship. So there are 3 degrees of freedom. For a diatomic, let's say 2 molecules are there. There's one linear relationship. The K stands for linear relationship. There's one linear relationship. F is equal to 3 into 2 minus 1. So 5 degrees of freedom. For a triatomic, there are 2 categories in triatomic. One is a non-linear, another is a linear character. In non-linear, there are 3 relationships. One is a 1, 2 and 3 relationship. So F is equal to 3 into 3 minus 3, which is 9 minus 3, 6 degrees of freedom. For a linear, there is 1 and 2, so there are only 2 degrees, 2 relationship. So it's 3 into 3 minus 2, which is 7 is the degrees of freedom for a linear one. So then I'll also tell you, these are about degrees of freedom. Then I'll teach you something which is very important. So then therefore you say that there is, next is equipartition, laws of equipartition of energy. This is very important topic, law of equipartition of energy. So there's just kinetic energy, as you know, and you know the formula is, for a monoatomic is 3 by 2 kBt. And this 3 by 2 kBt is the entire kinetic energy. You have to divide it by 3. So you get 1 by 2 kBt, which will be associated with one motion like Vx, not Vy and Vz. We have not included other vibration. So then there is equal partition of energy along x direction, y direction, z direction. Each energy absorption will result in each vibrations. Okay, so then let's take 3 by 2 kBt is the total energy which we have learnt, which has to be divided by 3 for 3 degrees of freedom. So for 1 degree of freedom, the energy associated with 1 degree of freedom is just 1 by 2 kBt. So you should know that there is the energy is equal in every direction. The energy absorbed is equally absorbed in every direction. So it's, it's half m Vx square. The total energy is half m Vx square plus half m Vy square plus half m Vz square, total energy which corresponds to 3 by 2 kBt. But you know that every energy is equally partitioned. Half m Vx square is equal to half m Vy square is equal to half m Vz square. So for every component will be 1 by 2 kBt. After dividing by 2 we got it, no? You have to write this here. This is known as law of equipartition of energy. And how do we define it? The energy gets distributed for every degree of freedom equally. The energy gets distributed among every degree of freedom equally. Okay, so for energy associated with 1 degree of freedom being 1 by 2 kBt. Are you clear? So therefore you understand the general formula. General formula for energy is degree of freedom by 2 kBt. Degree of freedom by 2 into kBt for 1 degree of freedom. So for one monoatomic, it's 3 by 2 kBt. For a diatomic, it will be, what was it for a diatomic? 3 to 6, 5 by 2 kBt. Like that you can write the degrees of freedom associated with any number. There is a general formula F by 2 kBt. Okay, so then next is to find the specific heat. To find the specific heat of, specific heat is nothing but delta U by delta T. We learned it in Mayer's formula. And which is d by dt of, U associated with, energy associated with a monoatomic is 3 by 2 RT. kBt is for molecule, RT is for 1 mole. So differentiated, this is capital T. dt by dt will become 1. So 3 by 2 R is Cv. And if you want Cp is Cv plus R. So it's 5 by 2 R. So gamma is Cp by Cv, which will result in 5 by 3. This is for monoatomic. So let's do this. Mono is done. Let's do diatomic. For diatomic, Cv is equal to d by dt of, you said 5 by 2 RT. So it's 5 by 2 R. And so then Cp is equal to 5 by 2 R plus R, which is 7 by 2 R. Therefore gamma is Cp by Cv, which is 7 by 5. Are you clear? Next is for a triatomic. Triatomic, you have two different ones. One is a 6 by 6 degree of freedom. Another is 7 degree of freedom. This is for linear and this is for non-linear. Remember, non-linear 6 by 2 RT. And this is for 7 by 2 RT. So find specific heat du by dt, which will be 6 by 2 R. With which you will add an R, it will become, if Cp will become, if you add an R, it will become 8 R by 2, is it? So then Cp by Cv is equal to 8 R by 2 by 6 R by 2. So 8 by 6, which is 4 by 3. Next for this one it's 7. Like this you can find the gamma for monatomic, diatomic and all that. Are you clear? So can I go to next one? It's for solids. So for solids, if you have to find the specific heat associated with solids, you should understand suddenly gases. Gases we took it as ideal gas. So we took only the kinetic energy. Here you have to take potential energy plus kinetic energy. So in this case, we know 3 by 2 kBT is the total energy, no? Which will get bifurcated as among this and this equally. So the total energy is just kB into T. Now, 3 times kB into T is the total energy, because this is 3 by 2 kBT plus a 3 by 2 kBT will result in just a 3 kBT. That is the total energy. And to find Cv, you can write it as RT also. You can write as 3 RT and differentiate this, you get 3R. And so what will be Cp, therefore will be 4R. I thought it was 5R, right? We got it as 5R. We saw Dulong and Petit's law also. It's 3R. Yeah, it's 3R only, sorry. Cv is just 3R for solids, correct. The graph it's not 5R, it's only 3R. They did a graph between Cv versus temperature, and they noticed that the graph was like this. At a higher temperature, they noticed that it was always a constant, which is 3R. Why it was a constant at 3R? Why is it becoming a maximum at this point? At higher temperature, the degree of freedom also becomes maximum, beyond which it cannot increase. But at a lower temperature, degrees of freedom is literally 0. Therefore, it's approaching 0. Are you clear? So, therefore, this is what Dulong and Petit also confirmed. They said that the energy is only dependent on the number of atoms, it does not depend on the mass of the atoms. Okay, that's what is concluding. And we know from here and all, we are only taking degrees of freedom. Nowhere we have included anything like a mass, which means energy is only associated with, or we can say the rise in temperature of a metal depends only on the number of atoms. Rise in temperature depends only on the number of atoms and does not depend on the mass. Okay, that's what is this specific heat of solids. There is also specific heat of water given in Aurora, but that's not in book. But you know, for water, you have to mark this up. There's a 3 kBT, which is for potential energy and kinetic energy. Both of them will be there in water. You have to multiply it with 3, so it will become 9 kBT. That will be the total number of vibrational energy in the case of water molecule. Water molecule has got in solids, you are not multiplying it with 3. But in water, you are multiplying it again with 3. That's the only variation. In solids, we are not multiplying with 3. We are just totally considering it as only as a potential energy vibration and kinetic energy vibration. We have not taken anywhere the x, y and z and all here. But molecules of water can have 3 degrees of freedom, 3 ways in which you can multiply and get this. You can also write it as 9 RT and differentiate, you get Cv is equal to 9R. And there again it's a constant. Can you see 9R is a constant for, that's all. And they will do a graph here again, which is for a specific heat versus temperature graph will be like this. Okay, remember this graph in case you need. The last but not the least is the mean free path. Mean free path, very, very important derivation. There's no paper without this derivation. Imagine a cylinder which consists of number of molecules. The cylinder's radius is d, in which you consider a molecule, an atom A or molecule A, which has got a radius d. The radius is d, whereas here the imaginary cylinders and the diameter is d, whereas the radius of the cylinder is small d. Okay, at any instant, consider all other molecules in the space is static. They are all having diameter d, but they are not moving. Only this molecule A is moving. Supposing it's moving through a distance of V into delta T, it would have gone through a volume of V into delta T into pi d square. It would have covered this volume. It's an imaginary cylinder, right? So pi d square, this is the volume. In the process, this molecule A would have collided with n molecules. N into, because n is the number of molecules per unit volume, so this many collisions it would have undergone. This gives you the number of collisions. Number of collisions in this particular volume. Now you should find mean free path, whose formula is the total distance traveled by the number of collisions will give you the mean free path. Total distance traveled is V into delta T by the number of collisions is n into V into delta T into pi d square. V delta T get cancelled, 1 by n pi d square. This is the mean free path, which is called the lambda bar. This is for just some molecules which are present only in the collision that's considering here. What about collision considering all molecules? They just randomly added a root 2 to the denominator and wrote it like this. Considering all molecules, write it like this. So from here, what you should do is you have to find what is m. You know, density is mass by volume, but this is considering unit volume. You can write capital M to be small m into n. Correct? Small m into n. Therefore, what is small m? Is density by m. Substituting that here is 1 by root 2 into density mele m pi d. You get a formula like this. So the mean free path therefore is inversely proportional to the density. Mean free path is inversely pi d square is inversely proportional to the square of the diameter of the molecules, and then the moving molecule. And then you also, this is not over. If you write like this, you get some marks, half mark. If you can remember, you have to continue. Do you remember that I wrote this formula? So you know, you write PV is equal to RT. Then write what is P from there, RT by V, multiplied by NA, and also divide by NA. So you write R by NA. You write R by NA into NA by V into T. R by NA is Boltzmann's constant. NA by V is small n into T. Therefore, you get a new formula for P, and you write what is n from this, P by KB into T. Take this and substitute it in here. You know, lambda bar is equal to 1 by root 2 into pi n d square. Pi n d square in n. In this we wrote n as like this. That's the first method. Then in second method we are writing n as 1 by root 2 pi P KB T opposite into d square, which shows that the mean free path is also directly proportional to temperature, inversely proportional to pressure. That completes the entire notes on mean free path. Okay, so if they ask you to say define mean free path, you know, it's a ratio of the distance traveled by one molecule by the number of collisions it suffered in a particular time. You can write it in your own words. So that completes this entire lesson. I'll upload the numerical video tomorrow.